So I want to start with a bit of motivation, something, maybe the origin of this problem I want to talk about. It concerns actions of Lie groups on spaces for which the orbits have a special structure, have a particular feature. So this is the origin of the problem or the question. Suppose we have a Lie group H, which we assume to be compact and connected for the moment, and we have a real vector space V, which is equipped with an inner product which is invariant under the action of H. Okay, so an H invariant inner product on this vector space. So I'm assuming we have an action of H on this vector space. This gives us, because the inner product is H invariant, this gives us a representation of H, an orthogonal representation of H on that vector space. Okay. So now let's pick an arbitrary point in V, or vector V, in the vector space. Then I denote by sigma V across the cross-section of the action at that point, which basically means, so we have the point, then the orbit through the point, and then there is a unique affine space which gives us the normal space of the orbit at that particular point. Yeah, so this is the cross section, sigma V. Yeah, the affine space, which is the normal space of that orbit at that point. And so such a cross section intersects actually all orbits. That's where the name originates from. And we say that this cross section is minimal precisely if the dimension of the orbit is maximal. So don't confuse this with minimal submanifold. This just refers to minimal dimension. Yeah? So a cross section originating from a generic orbit, so an orbit of maximal dimension, is called minimal. And then we say that this representation is polar if all orbits intersect a minimal cross-section orthogonally. See, in general, a cross-section intersects all orbits, and but there is no reason that such a cross-section intersects all orbits orthogonally. Yeah, this is quite a restrictive property. I think analysts are interested in this kind of problem, this kind of actions, because if you have a partial differential equation which is invariant under such an action, then you can simplify, you can reduce the variables and then investigate the PDE, so that simplifies the situation. So I'll give an example. The simplest example is the standard SO2 action on the plane. Yeah, so what is the orbit structure? We have a fixed point, the origin in the plane, and then the circles centered at that point. Maybe I draw a picture. So here we have a point which is fixed, and then we get all the circles which are centered at that point. Yeah, and it's clear what the cross-section is. So we take here an arbitrary, so what is an orbit of maximal dimension? These are the circles. So we take here a point, the circle. The cross-section is just the line passing through that point and the origin, and it's easy to see that this line intersects all other orbits orthogonally. So everywhere we have here perpendicular or orthogonal intersection. Yeah, and so this is the standard example of a polar action. There are more interesting such examples. Can we turn off the light again, please? Yes. So when we pick an arbitrary Riemannian symmetric space, G over K, and a point O in M, which is fixed by K, So this is, so we have the stabilizer of G at the point O is K. And then we can consider the isotropy representation on the tangent space of M at that point. Yeah, all the points, all the isometries in K fix the point O. Since they're isometries, these are orthogonal transformations of the tangent space of M at the point. So we get this bunch of orthogonal, so we get this representation here. And what one can show is that this representation is always polar. Yeah, so every symmetric space produces a polar representation via the isotropy representation. That's quite a large class of examples. And then there is an interesting result by Dadok from 1985. He actually proved that's all you can get, at least if you restrict to the orbit structure. He proved that when you have an arbitrary polar representation on Rn, so then this is orbit equivalent to the isotropy representation of a Riemannian symmetric space. So orbit equivalent means that the two representations have the same orbits. And that's quite remarkable. Somehow you see, you start off with this rather elementary definition and you end up with symmetric spaces. There is nothing whatsoever in the definition that suggests that there is such a strong relation to symmetric spaces. So it's really quite a surprising result. Okay. So this then suggested a more general definition in a more general context. We now fix or pick an arbitrary Riemannian manifold and we assume connected, and H is a connected subgroup of Rn, and we consider somehow the analogous situation. So we have a subgroup of the isometry group which acts on the manifold here, on the Riemannian manifold, and we can look at the orbit structure. And we say that then this action of the group on M is polar precisely if, well, geometrically we have the same picture. Namely, we have a connected and closed submanifold of the manifold such that this submanifold sigma intersects each orbit of the action. That's the first condition. Yeah. So sigma intersects each orbit of the action. And the second condition says that the intersection is perpendicular at each point. Yeah? So for every point of the section, the tangent space of the section is contained in the normal space of the orbit. That's what this terminology means. Yeah? So that means that the intersection is orthogonal at each point. So this is the generalization of polar action. One can prove, well, such a submanifold is actually called a section of the action. One can prove that such sections are always totally geodesic submanifolds. It's not difficult, it's a small argument using Killing vector fields. Yeah? So such sections are necessarily totally geodesic submanifolds. And there is a a special case when we assume that the section is flat, so is intrinsically flat, like that's a situation what we have in the Euclidean space. Yeah, every totally geodesic submanifold in Euclidean space is again a Euclidean space, basically, so it's flat. Yeah. So if we have this special situation, then the polar action is called hyperpolar. So that's a subset of polar actions. Okay. And the problem I want to talk about is the classification of such actions on Riemannian symmetric spaces. So I'm going to assume here that our manifold is a Riemannian symmetric space, like sphere, projective space over one of the normed real division algebras, Grassmannian, hyperbolic Grassmannian, spaces like these. Yes. And I want to talk first with about the compact case. So we'll assume that we have a compact symmetric space. And let's first talk about the rank 1 case. So our space is either a sphere or a projective space over non-real division algebra. And I think I will restrict here really only to the simply connected case. So what one can say in case of the sphere is, so when we have a polar representation on the sphere, that naturally extends to a polar representation on the Euclidean, on the Euclidean space in which the sphere is sitting. Yeah, it's just the natural extension of the action you have. So if we have a polar representation on a sphere, we get a polar representation on Euclidean space, but then every polar representation on the Euclidean space naturally induces a polar representation on the sphere because it's orthogonal, it will fix a point and something so on. You can show this. So one can apply Dardot's result, Dardot's classification, and basically one gets the same. That's what it means. Yeah, so there is nothing new happening in the case of a sphere. That's it. So it's more interesting to think about the projective spaces. I want to start with the complex projective space, describe what happens there. So this case of projective spaces was completely solved by Podesta and Torbergson in 1999. And in complex projective space, one can produce examples of polar actions by, in two steps. So what we take is a Hermitian symmetric space. Yeah? So it's a special class of symmetric spaces, those which are in addition equipped with a Kähler structure. So we pick a Hermitian symmetric space like a complex Grassmann manifold, what do I want to take, SO 2n over UN or us. And look at the isotropy representation of such a space. Now, since this is a complex manifold, the tangent space at a point is even dimensional. It's actually is a complex vector space. Yeah? So in the tangent space at the point, the sphere is odd dimensional. Yeah? So if we assume that our Hermitian symmetric space has complex dimension n plus 1, the sphere in the tangent space has dimension 2n plus 1. So we have a 2n plus 1 dimensional sphere. Now the isotropy representation of such a Hermitian symmetric space leaves invariant the usual S1 fibration one has on the odd dimensional sphere, which gives which are the fibers of the Hopf map onto complex projective space. So since this representation leaves invariant the fibers, this induces a representation or an action on complex projective space, and one can show that this is always a polar action. Yeah? So starting from a Hermitian symmetric space, using the Hopf map onto complex projective space, one can produce polar actions. It's straightforward to show. And what Podesta and Torbergson proved is this is all you can get. Yeah? All polar actions arise in this way, up to orbit equivalence. Yeah? So it's again isotropy representations of, in this time, Hermitian symmetric spaces which provide a complete answer to the classification problem. Yeah. So for quaternionic projective space, it's actually more subtle, the situation. You would think, well, the first intuitive idea, now replace Hermitian symmetric space by quaternionic symmetric space and do the same thing here by using the Hopf map on quaternionic projective space. But this intuition is wrong. Actually, something else happens here. So what one needs to do in this situation is the following. So we take a Riemannian product of quaternionic Kähler symmetric spaces. So it's a bunch of quaternionic Kähler symmetric spaces, and we take the product of them, and we assume that at most one of them have higher rank, which means that all but one of these spaces here, all at most, up to at most one of these spaces, are really quaternionic projective spaces. Yeah? So we take my quaternionic projective space times quaternionic projective space times quaternionic projective space, and so on, times, and then an arbitrary quaternionic Kähler manifold. Okay? So now when we have a quaternionic Kähler symmetric space, the stabilizer at the point decomposes into the product of two normal subgroups. There is an sp1 factor which produces the quaternionic Kähler structure on the manifold, and then complementary to this we have a subgroup Hi. This is how the stabilizer of a quaternionic Kähler symmetric space always looks like. And now we produce a group H by taking the product of all these groups H here, which arise in the stabilizers of these quaternionic Kähler symmetric space, and multiply it just with one sp1 factor here. So we get a group H. That's a definition. Well, so let's denote by n plus 1 the quaternionic dimension of this space which we have defined here. Then, since this is a quaternionic manifold, the real dimension of the sphere in this will be 4n plus 3. And this group H acts, then the group H acts on this sphere and leaves invariant these three-dimensional spheres which arise as the fibers of the Hopf map onto quaternionic projective space. And so now this action produces an action on quaternionic projective space via this Hopf map. Yeah, and one can show that this is again polar, and Podesta and Thorbergson proved that all polar actions on quaternionic projective spaces arise in this way. Yeah, so there it's already a bit more complicated. And finally, there is all this exotic case of a Cayley projective plane. So what they did, they explicitly classified the groups acting polarly on a Cayley projective plane. And first, this one observation is these groups one can get here, they act either with cohomogeneity 1 or 2. Cohomogeneity is the codimension of a generic orbit of the action. So cohomogeneity 1 or cohomogeneity 2 means that the principal orbit of these actions has either codimension 1 or codimension 2. Yeah? So it's either a real hypersurface or has codimension 2. And you see the actions one gets, there are 4 such actions of cohomogeneity 1, which are polar. The one is the spin 9 action, so this is the action of a stabilizer where one gets a point and then the spheres. These are 15-dimensional spheres, and typical to this will be an 8-dimensional sphere. So this is one polar action, and there are a few others. So I don't want to describe them in detail, it's just there is this complete list. Okay. So for higher rank, Kollross in 2002 was able to classify all hyperpolar actions on irreducible Riemannian symmetric spaces of rank greater or equal than 2. So again, to remind you, hyperpolar means that the section which intersects all orbits perpendicular is a flat submanifold. Yeah, this is a special situation where the section is a flat manifold. And he obtained a complete list. The methodology is actually not so difficult, because the group, you can assume that the group which acts is compact, and compact groups are well known. There is a classification of them, and then if you have a compact group, you look at actions of maximal subgroups. All these are known by Dünkin's classification. So it's a kind of a case-by-case consideration of all possible situations what you have, and so that produces a long case-by-case argument, and at the end you have a complete list. So that's the line of argumentation for here. So really that one can do this is so that one has the explicit knowledge of maximal subgroups of compact Lie groups. Yeah, that's behind this classification. It works here with hyperpolar. And then later Kollross proved, well actually this is a number of people proved this, that every polar action on an irreducible Riemannian symmetric space of compact type and rank greater or equal to 2 is hyperpolar. Yeah? this is quite quite remarkable, because what does this tell us? When we have a symmetric space of higher rank and a polar action on this, then the section must necessarily be flat. This is not obvious at all. And this is not true in the rank 1 case, because when you look at the examples that I explained on the previous slide, there are actions of higher homogeneity. See, what are flat submanifolds in a projective space? In a projective space, the only flat manifold you can find, which is totally geodesic, is just a line. It's a geodesic. There are no higher dimensional, totally geodesic flat submanifolds in a projective space. So a hyperpolar action in a projective space has necessarily cohomogeneity 1, but Podesta and Torvason, they produced more examples of higher homogeneity. So they are polar but not hyperpolar. In the higher rank case, polar implies hyperpolar, and that's quite remarkable. And what you see here is, that this is a number of people were involved in the classification. I mean, the first known classification was for the complex quadric here, and then for complex Riemannians, and so on and so on. And it was only recently, a couple of months ago, where Kollross and Litschak eventually solved the final case. So the compact case is well understood, at least in the irreducible case. For reducible manifolds, it's much more subtle. So one understands the situation quite well. In the non-compact case, what's already known since quite some time is what happens in a real hyperbolic space, and this was sorted out by Bing-Le Wu in 1992. So when we have a polar action on a real hyperbolic space, then up to orbit equivalent, we get only two possibilities. So what we do is, we consider the real hyperbolic space sitting inside the Lorentz space, so one of the usual models for a real hyperbolic space. Then an action on this real hyperbolic space extends naturally to an action on the Lorentz space. This is similar to when we have an action on the sphere, it extends to an action on the surrounding Euclidean space. So what Wu proved is that this polar action either acts in this way, so we have this group, this subgroup, SOK1 times H in the isometry group of real hyperbolic space, where H is a subgroup of a special orthogonal group of the remaining dimension here. So this acts, where this group H acts polarly on the Euclidean space of the corresponding dimension. So when we have such a group, so let me see, this acts then where H acts polarly on this sphere, which lives in the Euclidean space of dimension n minus k, which naturally sits inside Lorentz space of dimension k plus 1, on which this group acts, and then times Rn minus k. So we have the action of this group on Lk plus 1, this is transitive, and then we have H acting on this Euclidean space, and altogether we get the Lorentz space. Yeah? So we have somehow a decomposition onto something transitive on a smaller dimensional Lorentz space times something on a Euclidean space, and there we have a polar action. Yeah. And so we know these polar actions by Dadok here on Euclidean space, so then we get polar action on real hyperbolic space. Yeah. So somehow by decomposing the Lorentz space into a smaller dimensional Lorentz space times the Euclidean space, using Dadok's polar actions, one can produce these polar actions on a real hyperbolic space. That's one possibility. Or the other issue is, the other possibility is that the action leaves invariant a foliation of the Lorentz space by hyperplanes. So in this case, you see, when when we have a hyperplane in the Lorentz space, and suppose it intersects our hyperbolic space, so what we then get is either a sphere or a Euclidean space or a lower dimensional hyperbolic space, depending on how the hyperplane lies in the Lorentz space. Okay? So what one then gets is a reduction to an action on either a sphere or a hyperbolic space or Euclidean space, and they are all known. So these are the only possibilities. So that's what Bing Le Vu proved in 1992. So it's basically, again, what happens here is one gets a reduction to the known situation. That's all that happens. And that's all that's basically known. So I want to maybe summarize this a little bit and talk about what's compact versus non-compact, and a few say a few observations. Let's first think about actions of cohomogeneity 1. So when the generic orbit has codimension 1, then a section must have dimension 1. So the section, because the section is totally geodesic, it's a geodesic, so it's flat. Yeah? So we always have then a cohomogeneity 1 action is a hyperpolar action. Okay. Now, one can show that on every Riemannian symmetric space of non-compact type, one can find cohomogeneity 1 actions. But there are symmetric spaces of compact type which do not admit cohomogeneity 1 actions. Now, this comes out of the classification by Kollross. So there is really a difference between the compact and non-compact case, even for the case when the section is one-dimensional, so as simple as possible. Then polar and hyperpolar actions. So what one can show is that every Riemannian symmetric space of non-compact type admits polar actions which are not hyperpolar, and that's independent of the rank. Yeah, what I mentioned before is in the compact case and higher rank, every polar action is hyperpolar. This is no longer true in the non-compact case. One has examples. So the concept of duality, see what this suggests is compact symmetric spaces of compact type and non-compact type, there is a concept of duality between them. But what these two observations suggest is that the concept of duality is not useful for investigating polar actions. Yeah, because, I mean, you have actions in the non-compact case for which you don't have an analogon in the compact case. Yeah. So this concept of duality is useful only in very special situations. For example, if the group which acts is an algebraic reductive subgroup, then one can use the concept of duality and relate polar actions on a symmetric space of compact type with the corresponding dual space of non-compact type. Yeah? So for particular types of subgroups, one can establish a duality or a correspondence. And finally, and that's probably the most important one, see, in the compact case, one can restrict to actions of compact groups, and compact groups are really well understood. Whereas in the non-compact case, one needs to consider non-compact groups, and they are not really well understood. And that's the major difference between the compact and the non-compact case. And what I want to talk about here is how to get a strategy into this problem, into investigating non-compact groups and trying to classify polar actions on symmetric spaces. So this is maybe as a summary, the current state of affairs for the non-compact case. And I think there are three different cases to consider. The general case is that of polar actions, And in there we have the special case of hyperpolar actions, where the section is a flat submanifold. And among the hyperpolar actions, we have a more special case where the section is one-dimensional. Yeah. So this seems to be the most simplest elementary case. It's a bit more difficult, and that's the general case. So when we have such an action here, when we have an action of a group on a non-compact manifold, two things can happen. Actually, many things can happen, but it turns out it's useful to distinguish two geometric situations. One is when all the orbits form a foliation of the manifold. So all the leaves are diffeomorphic to each other. Or when we have an action with singular leaves. So what we get here is a singular foliation. Yeah, singular. This is, for example, that would be a singular foliation. Yeah, we have a singular leaf here. Yeah. So it makes sense to distinguish these two situations. They are geometrically different, and really when trying to classify these actions, one encounters different phenomena. So what we have for the cohomogeneity 1 case, we have an explicit classification for the case where we have a regular foliation, and we really understand, we sort of understand what happens in the singular case, but we can't actually write down explicitly all the groups. Yeah, that's where we have the problem. So this case we understand quite well. The hyperpolar case we understand also very well for the regular case, but the singular case is still, that's quite mysterious to us. We don't know what's happening there. Maybe to my talk on Saturday I will talk a bit about this, say where the problems are. And in the general case for polar actions, so what we have is always examples of polar and non-hyperpolar foliations, so they really exist. Yeah, we have many examples, but the only space where we have a complete classification is in the complex hyperbolic space. And for the even more complicated case, when we allow singular leaves, we have a complete classification only for the complex hyperbolic plane, and that's already so complicated that somehow you feel a bit, I don't know, it's not so clear what will really happen in the general case. Yeah. So all this is joint work with José Carlos Díaz Ramos from Santiago de Compostela and Hiroshi Tamaru, Hiroshima. With Tamaru, I did basically this bit here, and with Díaz Ramos is more or less this bit here. Okay. So the setup for what I want to talk about is this. Our space is a connected, irreducible Riemannian symmetric space of non-compact type. Like, for example, real hyperbolic space, complex hyperbolic space, complex hyperbolic, Riemannian. So G is the isometric group of the symmetric space, or let's say the identity component of the isometric group, and K is the stabilizer at a point. So then one knows that in this situation, G is a non-compact semi-simple real Lie group, and K is a maximal compact subgroup of G. Yeah, so one has a very special situation. And then by O, I denote the unique fixed point of K on M. So that's the terminology of the space. And then the group which acts polarly I denote by H, and I'm going to assume that H is connected and a closed subgroup of G. Okay. And this result here is not really a classification result. It sort of says a bit about the strategy, the different cases, and how to approach the problem. So that I proved with Tamaru last year. So we assume that H acts on the manifold with cohomogeneity 1. So we have a hyperpolar action where the section is a geodesic. So it's our situation. We have a polar action on the manifold, a hyperpolar action on the manifold with a one-dimensional section. So then we have four possibilities. So the first possibility is that the orbits form a Riemannian foliation. So this is the first case I mentioned. The second case is, well, they do, the other case is they do not form a foliation. We have singular leaves. So then this singular leaf may be totally geodesic or not. So I distinguish these cases. So the second case is that we have a totally geodesic orbit. So really nothing happened so far. It's just putting it in logical order with different cases. Yeah? So now assume that the singular orbit is not totally geodesic. And that's basically the main result of this theorem, as actually a theorem is. If there is a singular orbit which is not totally geodesic, then there are two possibilities for in which way the polar action or the hyperpolar action arises. Two ways it must arise. So one is that the action is orbit equivalent to the canonical extension of a cohomogeneity 1 action on the boundary component of the symmetric space. Now the boundary component, so what one does here is the symmetric spaces or non-compact manifolds, they admit many types of compactifications. And there is a particular one, it's called the maximal Satake compactification, which we need to take in this situation. And this maximal Satake compactification produces some boundary components of the manifolds. And every cohomogeneity 1 action on a boundary component extends to a cohomogeneity 1 action on the manifold. That's one way to produce examples. So see, the boundary components, when we have a symmetric space of non-compact type, a boundary component is again a symmetric space of non-compact type, but of lower rank. So this is a kind of rank reduction, which gives, which we get here. Or the fourth possibility is there is a construction method, which we denote by nilpotent construction, where one can produce some examples. So this is a sort of rough scheme for how to get these actions, and I want to describe this now a bit more in detail so that you see what the phenomena are that arise in there and the problems. So I want to go through these four cases and explain this in a bit more detail. Yeah. So the first case is that of a foliation. So we are now in the situation that we have this symmetric space of non-compact type, and we have a group acting on this symmetric space such that the orbits form a foliation of codimension 1. So then I denote by MF the set of all such foliations up to isometric congruence. Yeah, I do not distinguish between two foliations when I can map them into each other by an isometry of the space. Now that's not interesting. Don't want to distinguish these. So then what we prove is that the set of all such foliations can be parametrized in this way. We have a real projective space of a certain dimension, union with a set of R points, and that modulo or factored out by some automorphism group. So what are these objects in here? The number R is the rank of the symmetric space. So the rank of the symmetric space, this is the maximal possible dimension of a Euclidean space which you can embed isometrically as a totally geodesic submanifold into the symmetric space. Yeah, so this is the rank. So for the given symmetric space, this is a uniquely determined positive integer, this rank. Now the symmetric space, as I mentioned before, is a homogeneous space is G over K, where G is a semi-simple Lie group. Semi-simple Lie groups can be described nicely in terms of root space decompositions. Yeah, there is this characterization of such Lie groups in terms of root spaces, root space decompositions. And so to every symmetric space of non-compact type, one can associate a root space decomposition, and to these can be described in terms of a Dynkin diagram. Yeah? So the symmetric space determines a Dynkin diagram, and such a Dynkin diagram has an automorphism group. There are only three possible types of Dynkin diagrams when we have a symmetric space of non-compact type, which I actually assume to be irreducible. I didn't write this here. So there is either no symmetry at all, or there is a Z2 symmetry, or there is a symmetry group of the group of a set of three letters. So when we have a Dynkin diagram of this form, yeah, so there we have a symmetry group S3. These are the only possibilities we have here. So, so what this result says here is that the parameter space, or the homogeneous codimension 1 foliations on a symmetric space of non-compact type depend only on these two invariants, the rank of the manifold and the automorphism group. Okay. And I want to explain how they are constructed in a minute, but first an observation. So when we are in the most simplest case, namely when R is equal to 1, the rank is 1, we have a hyperbolic space over a normed real division algebra. There's a real hyperbolic space, a complex hyperbolic space, quaternionic hyperbolic space, or Cayley hyperbolic plane. So what does this tell us here? R is equal to 1. We have a zero-dimensional real projective space. This is just a point. And here we have another point. So we get 2 points here. And then, so when we have rank 1, the Dynkin diagram is just 1 point. So there is no symmetry. That's the identity. So we get just 2 points here. Yeah? What this tells us is that on a hyperbolic space, there are exactly 2 non-congruent homogeneous codimension 1 foliations. And here they are. This is the picture for the real hyperbolic plane. Yeah, think of the real hyperbolic plane. This is the simplest example as rank 1. So here we take the Poincaré model. One foliation is the foliation by horocycles. That's a homogeneous codimension 1 foliation. And the second foliation you obtain by, here is a geodesic, and then all the curves which are equidistant to the geodesic. Yeah. So these are the only two homogeneity, or the only two homogeneous foliations you can get on a real hyperbolic plane. But whatever hyperbolic space you choose over whatever dimension and whatever normed real division algebra, you get the same picture. So we get always a horosphere foliation in one case, and in the other case, well, you see the geodesic for the real hyperbolic plane we have to replace by something else, and this something else is normally, that's a minimal submanifold. One can explicitly describe what this is. In the case of a real hyperbolic space, this is actually a totally geodesic hyperplane. In the case of complex hyperbolic space, so this here is, it's a minimal, it's a ruled minimal hypersurface which is associated to a horocycle in a totally geodesic real hyperbolic plane. Yeah, so what we do is, here is a real hyperbolic plane, pick one of these horocycles, then put this whole real hyperbolic plane into complex hyperbolic space and produce from this the ruled hypersurface. Now this is exactly what you have to put here, and then you take the equidistant hypersurfaces. Yeah, this is how you get the second one, second foliation. So another observation is, I mentioned this, let me here, this is also interesting here because you like to work here on the Grassmannians. So what does this tell us for complex hyperbolic two-plane Riemannians? So we're looking at this space here, the non-compact dual of a complex two-plane Riemannian. So in this case, the Dynkin diagram is of type BC2, and these are the multiplicities. Yeah. So what is the setup here for the Dynkin diagram and the root system? So we have rank 2. The root system will be defined on a two-dimensional vector space. And this is the standard, this is the root system which we get here. These are the usual one forms on R2. One can describe this. Then one has the positive roots. So there are 6 positive roots, and they have some multiplicities. We have simple roots, alpha 1, alpha 2, and all this produces exactly this Dynkin diagram. Yeah, we have 2 simple roots. Then here we have the corresponding multiplicities. Yeah, and so we can then work out what do we get. When R is equal to 2, we get RP1. This produces one set of foliations, so it's an RP1 of foliations. Then we have the set of 2 elements, and the automorphism group of the Dynkin diagram is trivial. There is no symmetry. Yeah? So for a complex hyperbolic two-plane Riemannian, this is the parameter space for the homogeneous codimension 1 foliations. And one can describe them explicitly. Yes, so another observation is, I mentioned this before, this parameter space depends only on the rank and on possible duality or triality principles on the symmetric space. So for example, if we assume that the rank is 8 and the automorphism group is trivial, so the Dynkin diagram has no symmetry, then this is the parameter space for these foliations, RP7 union with 8 elements. And there is really quite a large list of symmetric spaces which of rank 8 and trivial automorphism group for the Dynkin diagram. I've written them all down here. Yeah? So there are these 1, 2, 3, 4, 5, 6, these 7 symmetric spaces here, and then there are 3 series of symmetric spaces, hyperbolic Riemannians over the real numbers, complex numbers, and quaternionic numbers of particular, 8-dimensional subspaces in these particular spaces. So what is remarkable here is that for all these spaces, the parameter space for the homogeneous codimension 1 foliations is the same. There's really no reason for this, why this should be. Yeah, they're geometrically completely different. So the way to construct them, this comes from the Iwasawa decomposition. So when we take the Lie algebra of the isometry group, this has when we pick an arbitrary Iwasawa decomposition of this, so k plus a plus n, k is the Lie algebra of the isometry group, a is a maximal abelian subspace in the orthogonal complement of k with respect to the killing form, and then n is some nilpotent algebra, which in terms of root spaces is just the direct sum of the root spaces corresponding to positive roots. Yeah? So this is nilpotent, this is abelian, this is compact. And you see what you get from the Iwasawa decomposition is that our symmetric space is G over K. So when we factor out K here, we have G over K. What is left is A plus N. And A plus N is a solvable Lie algebra. When we exponentiate, we get a solvable Lie group, and this gives this solvable Lie group acts simply transitively on the symmetric space. So what this Iwasawa decomposition actually produces is a model of the symmetric space as a left invariant, as a solvable Lie group equipped with a left invariant Riemannian metric. Yeah? So every symmetric space of non-compact type actually can be realized as a solvable Lie group with a left invariant Riemannian metric, and that comes from the Iwasawa decomposition. Now what we do is, so we take the A plus N part here, and we pick now a line in the real projective space Rpn minus 1. You see A is an R-dimensional vector space, has real dimension R. So we identify RPR minus 1 with a real projective space of A. So we can take the orthogonal complement of this line in A and we add n. What we get is a subalgebra of A plus n of codimension 1 in A plus n. So when we exponentiate this subalgebra, we get a group acting on the complex, on the symmetric space with codimension 1, homogeneity 1. So this produces a foliation. Now, this has no singular leaves. And all these leaves are congruent to each other. So this is one way to construct such foliations. And that's it's just a comment here. If the rank is greater or equal than 2, then some of these foliations are harmonic. So all leaves are minimal submanifolds, and so they produce a harmonic map from the symmetric space onto the real numbers, where the real numbers is just the space of leaves. Yeah, so it's the natural projection from the symmetric space onto the space of leaves. That's the harmonic map in this situation. So the other foliations coming from the set of R elements are constructed in this way here. So we pick a number I in here. This corresponds to a simple root in the root space decomposition. The simple root has a root space which lives in N. So one of these root spaces will be G alpha I. So we take a line, a one-dimensional subspace in this simple root space, and then take the orthogonal complement of this in N and add A, and again what we get is a subalgebra of codimension 1. We exponentiate, look at the orbits, what we get is a foliation Fi of M. Now what one can show is that this construction is really independent of the choice of this subspace. They're all isometrically congruent to each other. So one really gets, for each such integer, one gets only one foliation, up to isometric congruence. And each such foliation has exactly one minimal leaf. And what one can show, that's just a comment here, if the two roots have the same length, then actually these two foliations, or the hypersurfaces in these foliations, have the same principal curvatures with the same multiplicities. So one understands the geometry quite well. And this is one corollary of this, is if the rank of the symmetric space is greater or equal than 3, one can produce from this non-congruent homogeneous hypersurfaces which have the same principal curvatures, counted with multiplicities. Yeah, and that's quite remarkable. What this means is one cannot distinguish homogeneous hypersurfaces just by their principal curvatures. Yeah. And the simplest example is in this symmetric space, SL4R over SL4, which can be realized as, which is just the set of all upper triagonal matrices with real coefficients and determinant 1. Yeah, so this is a symmetric space of rank 3. The Dinkin diagram is of this form. And there we see we have a symmetry, a Z2 symmetry. Yeah, we can just reflect in alpha 2. So they all have the same length, these roots. Alpha 1 and alpha 3 produce the same foliations, but alpha 2 will be a different one. And the foliations I wrote down here, they're very elementary. So what happens in the case what is produced from the first root, alpha 1, we got the foliation, or one leaf of the foliation we obtain. If we just insert the 0 here, and everything else remains the same, the foliation we get from alpha 2 is we obtain by inserting a 0 here. So these are two examples of hypersurfaces which are non-congruent, but have the same principal curvatures. Yeah, so that's an explicit example. So maybe then that's the last slide for today. It's the case of a totally geodesic singular orbit. It's the second case I had in this result with Tamaru. There we have a complete classification. So what we can show is that F is a totally geodesic singular orbit of a homogeneity one action on the manifold, precisely if this submanifold is reflective and the rank of F perp is 1. Now what does this mean? A submanifold is reflective if the geodesic reflection in the submanifold is an isometry. Yeah. So this is a special type of totally geodesic submanifold. So when we have a reflective submanifold, then the tangent to the normal space, we have another totally geodesic submanifold. So you can think of like you have an affine subspace in Euclidean space. The reflection in this is an isometry. So we have this affine subspace, and perpendicular to the affine subspace is another affine subspace. Yeah. Or when we are in a sphere, so we have a lower dimensional sphere, a k-dimensional sphere. Perpendicular to this, we have an n minus k-dimensional sphere. Yeah, so this is the general situation. So here we are in a situation, so we have such a submanifold, reflective submanifold, and these reflective submanifolds were classified by Leung in 1974. And so what we need here is just the condition that the rank of the submanifold which is perpendicular is 1, so that this is a hyperbolic space. So one can write down a complete list of such submanifolds. But amazingly, there are a few totally geodesic submanifolds which are non-reflective and can arise as orbits of homogeneity 1 actions, as singular orbits of homogeneity 1 actions. And I've written them all down here. There are 5 such totally geodesic submanifolds. This is the symmetric space. This is the totally geodesic submanifold, which is non-reflective. And here are the corresponding dimensions. Yeah, so for all these 5 types, there exists a homogeneity 1 action such that F is a singular orbit. What is remarkable here is that all these exceptions are related to the exceptional Lie group G2. There's G2 here, 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 and there. I don't know why this is quite mysterious. So what we proved is, basically what this gives us is a classification of all the homogeneity 1 actions which have a totally geodesic singular orbit. So this case we understand well. We have a complete list. So then there is the remaining case, and that's the interesting case, where the singular orbit is not totally geodesic, and that's where I want to start with in my next talk. Thank you for your attention.
Do you have any question?